Great. So now we're going to shift gears a little bit into hearing some science talks that have been that were submitted from 6 folks in this next block of talks that are all somehow related to using observations as a statistical constraint on models, using different statistical approaches, some of which might fall into what people typically call AI, and some of which are different from that. So we're going to kick this off. Before we get started, let me just say each of these talks is 15 minutes. So I'm going to ask the speakers to please try to monitor the time and finish a couple of minutes earlier than that, maybe around 12, so that we have some time for questions and transitioning to the next speaker. And also, I want to introduce the 2 folks who are co-moderating this session with me. So that's Marcus van Leer-Welke here and Nicole Reamer. And we're going to take turns introducing the speakers and moderating the Q&A. So if you have questions, put those into the chat, or we'll also keep an eye on the Q&A, and you can do that either during the talk or at the end. Okay, great. So now I think I can introduce our first speaker for this next set of talks, which is Sam Silva. And Sam had done his PhD in atmospheric chemistry at MIT with Colette Heald, working on various issues, including some work on machine learning to understand ozone dry deposition better during his graduate work. And now he is a Linus Pauling Fellow at the Pacific Northwest National Laboratory, where he is working on AI in interactions between land and atmospheric chemistry. So go ahead, Sam.
All right, great. I expect that my screen sharing should be working well now, and title slide and everything. To get started, thanks for giving me the opportunity to speak. And today I'm going to talk to you about a project I'm working on with some others here at PNNL and elsewhere on developing physically regulated emulators, regularized emulators of aerosol activation. So I'd like to get started first by sort of giving a broad sense for the scientific problem we're interested in solving here. And it largely relates to the fact that aerosol-cloud interactions are a large and potentially the largest uncertainty in our modern understanding of the climate system. And I think that's nicely illustrated by this figure from the IPCC in 2013, looking at a bunch of different forcing agents in the radiative forcing of climate and their associated uncertainties. And if you look down here at the very bottom, and highlighted in a red square, you can see that rectangle, you can see aerosol-cloud interactions are this negative blue bar. And it turns out they have the largest uncertainty out of any of the associated forcing agents here. And so for this reason and many others, the scientific community is very interested in nailing down exactly what's going on with aerosol-cloud interactions and doing a better job simulating these processes in models. Aerosol activation is a critical component of these aerosol-cloud interactions. And aerosol activation is the activation of aerosol particles in the atmosphere into cloud droplets. It turns out in the atmosphere that the direct formation of cloud droplets through the nucleation or through the condensation of liquid water onto itself to form a cloud droplet, that droplet is thermodynamically unfavorable. And so the vast majority of cloud droplets form through the condensation of water onto aerosol particles that exist. And the classic example of this that many of us may have seen in our coursework is ship tracks. As a ship sails underneath a cloud, the emissions of aerosol from the combustion engines in those ships lofts up into the cloud, and those aerosol then get activated into cloud droplets. More droplets are formed, and there are these bright tracks that you can see here in this image in the background. The direct simulation of aerosol activation is too computationally expensive to routinely use in Earth system models. It takes far too long because you're trying to resolve far too many small-scale processes. And so there's a lot of work working on trying to develop high-quality emulators of this process. And we're interested in how we can use machine learning to help with this. I'd like to first start by sort of giving a scope of the field pre-machine learning and what exists there. And the take-home message here is that existing emulators involve some very strong trade-offs between computational accuracy and speed. And so what I'm showing here is a figure from Steve Gann's 2011 review paper, looking at the number fraction of aerosol activated on the y-axis, which is largely the target quantity that we're interested in emulating properly. So the fraction of aerosol that actually become activated to cloud droplets, adds a function here of number concentration, but it varies with a wide variety of parameters. And the blue line is this numerical model. This is the type of model that's far too expensive to run in Earth system models. And these other 4 lines represent different parameterizations that are that have various trade-offs in terms of process representation and speed. For the purposes of this talk, I'm going to be talking about the numerical model and the ARG scheme, or a numerical model similar to the one used here. The ARG scheme is comes from the Abdul Razak and Gann series of papers, and our input was a variety of aerosol and meteorological parameters, and our training data set was 20,000 realizations of this numerical detailed model, Latin hypercube sampled through that input space. I'd like to first just sort of note how the ARG scheme performs. This is just sort of the traditional parameterization. You're looking at the parcel model, or the detailed numerical simulation on the x-axis, and the ARG parameterization on the y-axis. The red line is 1-to-1, and the blue represent 2-to-1 and 1-to-2. And what you can see here is that generally do a pretty decent job, although there is pretty substantial scatter. If you train a fairly simple feed-forward neural network with just a few layers and drop out after each layer, you get something that looks like this, which is, of course, much better, right? Much more closely clustered around the 1-to-1 line with far fewer outliers. I'd like to note that we did try other machine learning emulators as well, ridge regression, XGBoost, and so on, and the deep neural network performs the best. And so that's what I'll be talking about for the rest of this, this presentation. So we had this question of how can we improve the accuracy of this neural network further, right? Because we really want to nail down exactly what's going on in this process. And an idea that we had that's fairly simple is to use something called physical regularization. And here we're using a very simple technique for adding this physical regularization. And so what regularization is the process of adding information in order to help solve an ill-posed problem or prevent overfitting in your technique. And so I have a little bit of a map of how we do this, or a diagram. The traditional way of running machine learning, this is what you might learn how to do in, for example, a Coursera class. You take a set of inputs, use that to drive your machine learning model, and you make a prediction. Here, the activated fraction. And this is sort of physically naive, right? It doesn't have there's no known physics incorporated into the machine learning model or the training. In our case, we regularize physically this system using just a simple additive scheme where we first calculate the activation fraction from the ARG scheme, and then calculate an addition to that activated fraction that helps best produce a prediction of the parcel model. And so this is physically regularized. If you think about this from a different perspective, you could think of this as residual learning. You're learning the residual of the ARG scheme, a bias corrector to the ARG scheme, or as we heard in the last talk, a sort of augmentation type application of the surrogate model. And here we can just basically show that the addition of this physical regularization improves emulator predictive skill. So what you're looking at here on the left is a base deep neural network. I've shown you this plot already. Performance is fairly good. When you add the regularization from the ARG scheme, you end up with a much tighter simulation, right? We're much closer to the 1-to-1 line and even fewer outliers, which we're really excited to see. Additionally, adding this physical information gives a lot of performance gains in edge cases. So here I've just zoomed in the previous figure to now the bounds of 0 to 0.1 instead of 0 to 1. And you can see that the base deep neural network actually overestimates quite a bit in this very low range. And this comes from the fact that we're training to optimize the mean squared error. And so these relatively large differences in small numbers don't contribute nearly as much to that optimization function. And so this, the training doesn't necessarily care about this. But when you regularize using the ARG scheme, you end up with a much better looking distribution in this lower region as well, which is quite nice. As it turns out, actually, in the atmosphere, large differences in these small numbers can have a pretty substantial climate effect. And lastly, the physical regularization improves our generalizability in a 4 Kelvin test case. So we developed this pseudo generalizability test where we took our training data set and looked only in cases that were 4 Kelvin warmer than that, still sampled throughout the rest of the input space with light and hypercube sampling. This is sort of a pseudo climate change type generalizability, right? You're looking in a case where your model was not trained. And the base deep neural network is shown here. Performance is fairly good, and it gets even better when you regularize with the ARG scheme, where almost every point lies very close to that one-to-one line. So we're pretty happy to see this. Of course, this is a case study, right? It's sort of a test case demonstrating the value of this sort of technique, but we're really interested in what these emulators actually look like in a real climate model. So to do that, that's a fairly complex challenge from an engineering perspective. So we first implemented the base deep neural network into E3SM, which is the climate model many of us use here at PNNL. And the results are really exciting. Essentially, we can get it into E3SM, the model doesn't blow up, the model doesn't crash, and it looks like planet Earth, which those of you who've tried to implement neural network emulators into Earth system models know this is certainly not a guarantee. So what I'm showing here is the annual average precipitation rate from a set of simulations using the base deep neural network here on top and the traditional version of E3SM on the bottom. And basically these maps look very similar, and that's very reassuring to us. And we're really excited that we can actually get this running online in a real climate model with things like topography and so on. Of course, not everything is perfect. So the base deep neural network performance leads to way too many cloud droplets. So I'm showing here a figure of some difference plots. The base deep neural network on the top, E3SM, the sort of traditional version in the center, and the difference on the bottom. You can see the difference is almost entirely red, meaning that the base deep neural network vastly overestimates the number of cloud droplets as compared to the base version of E3SM. And this is not ideal because we think to begin with, E3SM actually potentially has too many cloud droplets before the addition of the neural network. So in terms of looking at the effective radiative forcing of aerosol-cloud interactions, I've shown, I would just put 3 bars here. On top is the estimate from the IPCC. The traditional E3SM is in the center, and you can see that's already on the high side of what we might think of. And the basic neural network is even higher. So this certainly is not a perfect solved problem yet, but we're really excited that we're able to actually get this into the model and start doing some science. And so the take home and lessons learned and next steps that we have from this are that physical regularization in our very, very simple way that we've implemented it is a pretty simple and effective strategy that actually improves your emulator performance. I didn't talk about it here, but the quality of that physical information does matter. So if you put, for example, a worse regularizing term that does a worse job of emulating aerosol activation, you get a worse result. And it's important to consider the use case of your emulator prior to design. So if we're just trying to optimize based off the mean squared error, we can get a very good performance. But if we are trying to, for example, actually optimize this performance in a climate model, you need to consider that when you're actually designing your emulator. So the next steps here are to address the cloud droplet overestimation behavior. We think it is an overestimation. We want to make sure that we can sort of fix that and invest some of the causes of the poor model predictions. I think some of these new explainable methods that we're going to hear about throughout the rest of this workshop could be very exciting for that. So with that, I'd just like to say thank you, and I'd be happy to chat offline and right after this talk. Great.
Great, thanks, Sam. I think we can take a question because I used up a little bit of your time at the beginning. So we do have a note in the chat from Scott Collis saying, very nice work. And a couple questions coming in. Just want to remind the audience as well, actually probably the best way to give us questions is to make them visible in the chat to all attendees and just put them into the chat. So can you say a little bit, Sam, about how you do the physical regularization? That's the main question that we had here.
Right, so this is done simply through, instead of learning the mapping from the input to the output space, we're learning the difference between the true value we want and the prediction from the ARG scheme, and then adding the ARG back into it. So this is a simple additive model where we first calculate the ARG predicted, let's see if my slide can help with this. I don't know if I can go back to it, but we simply calculate the droplet, the aerosol activation using the ARG scheme, and then calculate a sort of residual term or addition to that to get us closer to the truth.
Great,
I'd be happy to
thanks.
show you that, state that mathematically if you're interested later.
Yeah, I think we can let other questions either go to the chat. You can keep answering them in the chat or offline, and then we can switch to the next speaker.